Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called Ohm's Law and also electrical current. So first of all, we're going to talk about materials for a moment. So materials can be classified as one of two types. You have conductors. Oops, and I'm going to draw that in a color that's a little easier to see. Conductors and insulators. All right, big deal about a conductor. Conductors will allow charge to move. Insulators will not. So examples of conducting material, metals are the main examples of conducting material. Aluminum, copper, anything with one or two electrons in its outer shell typically will conduct electricity pretty well. Solutions, though, where maybe you take some salt and throw it in some water, and the sodium chloride breaks into sodium ions and chlorine ions, that will conduct electricity as well. Now, for the sake of this example, what we're looking at up here, imagine this. This picture is made of a material that's somewhere in between these. Not a perfect conductor, not a perfect insulator. A material that will conduct given a little effort. Right? And now, let me clear this out of here. So now imagine that we connect this battery, positive terminal at one end, negative terminal here to the other end. Now, as I always like to do, I'm going to go ahead and color code the potential. It's very important to realize that this would all be one potential. This is conducting material up to this point. This is not conducting material. Therefore, there could be electric fields in this region. In fact, there will be electric fields in this region. And therefore, my constant potential would end right there. Right. Now, imagine that this material has positive charge carriers and negative charge carriers free to move. And we want to take a look at this situation and see what's going to happen. Now, notice that the right-hand side here, this is the positive terminal of the battery. The right-hand side is at a higher potential than the left-hand side. So what is going to happen inside of this material is it's going to set up an electric field. Remember that electric field is, electric potential is field strength times distance. So what we're going to have is oops, I'll draw those in a different color. I'll draw those in red. We're going to have electric fields set up that are basically going to be from right to left. And remember that the difference in potential between 2 points, delta V, is field strength times distance. And again, written like this E would be kind of like the average electric field within a region. We know we have a potential difference between this point, and then this would be the relative distance. So we know there'd be an electric field between there. Now, the electric field would point right to left because the right-hand side of this is at a higher potential than the left. So a very important thing is going to occur here. Let me label these. These are electric field vectors. The positive charge, these guys are going to start moving in the direction of the electric field with some speed. Now, when I say they're moving to the left, it's not quite like that. If I were to track a charge carrier, its motion is very chaotic. They're just kind of moving all over. But overall, they would kind of move to the left. And the speed at which they're moving to the left is called drift velocity. All right, these negative charge carriers, again, highly chaotic motion, but overall, they would move to the right. So the positive charge overall would be shifted left. The negative charge shifted right. So if I were to pick a cross-sectional area and wait a certain time, a certain number of charge carriers are going to pass through that. Pluses are going to move from right to left, and minuses are going to move from left to right. The rate at which charge is moving through that area has a special name. It's called electric current. Electric current. And this is how I define it. It's rate that charge is transferred, or I'll just say rate that charge moves. Right? Mathematically, the average current going through that cross section, here's how it would be calculated. Current is usually represented with the letter I, and it's equal to delta Q over delta T, where again the delta Q would represent the total charge transferring through this cross section at any given time. And therefore current would have units of coulombs per second. And like most things in physics, 1 coulomb per second has its own special name. 1 coulomb per second is called 1 ampere. A-M-P-H-E-R-E, usually just called an amp. Now, in this example, you'll notice that we have positive charge moving left, negative charge moving right. So you can have an electrical current with either positive or negative charge movement. The standard adopted for sign convention is positive charge movement. So in this example, the positive direction for current is this way, to the left. So we would say that this has an electrical current to the left. Whether we are talking about the positive charge moving right to left or negative charge moving left to right, the positive current direction would be from right to left. Pardon me. Okay, so now let's talk about in metals. In metals, the material or the charges that are free to move are electrons. So if this thing were purely a metal, a conducting surface, all we would have would be these negative charges moving from left to right. But this still would be the positive charge direction for that current. So we've got current is delta Q over delta T measured in coulomb per second. If we think about what's creating the current, it's the electric fields in this region, which are set up by the voltage of the battery. The fact that we put a potential difference between these two sides sets a field up. That field is what drives current through this region. So in effect, the current depends on voltage. Now, it's not too hard to show that if we increase the voltage, we increase the current. And it's a pretty easy experiment to show that if we double the voltage, we'll double the current. Or if we triple the voltage, we'll triple the current. So it turns out the current is directly proportional to the voltage. So I'm going to put equals delta V here. Right? But depending on the geometry and material here, this material has a property called electrical resistance. The electrical resistance of the material is just like its name implies. It's the resistance of the material to allowing charge to move through it. If we think about what it depends on, well, it's a function of the material. Materials like metals would have very low, if this were made of a metal, it would have low electrical resistance. It's a function of the length of this object here. Typically, the longer the object, the lower the current. Therefore, the longer the object, the higher the resistance of this object. And it's a function of the cross-sectional area, meaning if we're looking this way, the larger that cross-sectional area is, the easier it is to push current through it. So, electrical resistance gets bigger with length, but it gets smaller with area. So we can actually write a little equation for this. The electrical resistance is directly proportional to the length, meaning equals some constant times the length, but falls off with area. Now, the electrical resistance hinders current. So over in this equation right here, the electrical resistance, the electrical current is inversely proportional to the electrical resistance. This law that I have written out, which when you look at your textbooks probably will be written like this, delta V equals IR, is called Ohm's Law. Very important law for the analysis of circuits. If we take a look at the electrical resistance term here, resistance is equal to voltage over current. So it has units of volts per amp. And like most things in physics, 1 volt per amp has its own little pet name. 1 volt per amp is called 1 ohm. There's this symbol for an ohm, this little headset looking symbol. So if we think about what resistance means, resistance is just like its name implies. It is an object's resistance to current, meaning that the higher the resistance it has, the lower the current overall will be. Resistance is measured in volts per amp. So for example, a resistance of 5 ohms means it takes a 5 volt current or 5 volt voltage to get a 1 amp current. A 20 ohm resistance would mean you need 20 volt potential difference to get a 1 amp current, and so forth. Ohm's law is just a mathematical law stating basically that the current through a system is proportional to the voltage, but is inversely proportional to resistance. So hopefully this video reasonably well describes concepts of electrical current, and I'm going to make a bunch more with how current relates to circuits and how Ohm's law is applied to circuits. Have a great day.